All right, we're live. Hello, hi, good afternoon, everybody. How are you doing today? I can see so many people are here in the chat already. Well, hello, Ayush. Hi, Ifat. Hi, Anuj. Hello, Nikita. Good afternoon, guys. So, here I am yet again with another brand new one-shot session for NEET 2022 series, right? Yes. And today we are going to continue with, of course, dual nature, where we are going to concentrate on dual nature of radiation and photoelectric effect. Alright, so as I've told you before as well, let's buck up and let's get started. But well, before we get started, hello Vaishnavi, hi Vasu. Guys, come on, tell me quickly, am I audible? Am I visible properly? If I am, give me feedback, give me a thumbs up so that we can get started with the session. Alright? Come on. Tell me, am I audible? Am I visible? Is everything okay? Hello Roshan, good afternoon. Hi Nikita. Yes, okay, alright. I have got the feedback. Gayatri says yes. Great, great. So, now that everything's good, technically no issues whatsoever, let's get started. I am really excited because, well, as I've told you yesterday as well, right? Modern physics, one of the units where it is very, very easy, whichever competitive exam you're talking about. Alright, so the questions that come, whether you're talking about NEET or you're talking about JEE Main, the questions that come from modern physics are very easy. Direct application of concepts, of formulas, and very scoring topic, right? It is a very scoring topic. So, now, without further ado, let's get started. Alright, Astha is asking, ma'am, aaj menti nahi hai kya? Yeah, Astha, today we have another one-shot session. Alright, not menti, but don't worry, in between of sessions, I do have questions here and I will give you exact 60 seconds to solve these questions. Alright, so there will be practice, you will learn application of fundamentals, right, along with learning about fundamentals. So, bright future, you are a new student, great, welcome, and let's start with this session. Afterwards, you should go back and look at or study from the other one-shot sessions that have happened as well. Alright? Okay, alright, let's get started. Today we are going to cover these three subtopics in our session. Okay, so we are going to cover photon theory. Yesterday we did a little bit of introduction to photon theory. Today we are going to delve a bit deeper. Okay, then we are going to go to radiation pressure and then we are going to go to photoelectric effect and we are going to do a complete post-mortem of all of these subtopics. Alright, Usha, yes, I understand you're a new student. Welcome over here. Let's get started. Sharmila, good afternoon. Hi Shreya. Hello Pratihar. I can see you all are here. Hello Rishabh. Good to have you here. Now, the first subtopic that we have over here, right? Oh, Ayush is also here. Hello Ayush. Okay. Now that we have, well, we've had our initial hello, hi and good afternoon, right? Let's get started. Okay, Bright Future is saying something. Ma'am, aap animation ka through padhate ho kya? Yes, yes, there are animations in this PPT because, well, visually, if you understand something, right? If you get to see something in animation, it's good for you. You understand it better, right? So it helps in understanding. All right. Usha Ghoshal, my real name is Indranil. Alright, Indranil, I'll understand that. So, you are using somebody else's account, I understand, right? Okay. Mehtab. Hello, Mehtab. Rangan says, I really like your teaching. Thanks, Rangan. I hope this is helping you, right? So, that's what I want at the end of the day. You guys should learn really well and practice at the end. Okay, so don't forget to practice. Chalo, alright, bright future, Vaishali. Okay, hi Vaishali. Okay, let's start. Enough chit chat, let's start. So, now let's start with photon theory. As I've told you before, yesterday we had a small very small introduction to photon theory, right? So we understood that, yes, in 1900, Max Planck gave the quantum theory of light, right? And he said that all electromagnetic radiations are quantized in the form of wave packets of quanta, right? In light, those wave packets, those energy packets are called photon. Okay, so we understand that for light, for all electromagnetic waves, the energy comes in the form of photons. Photons are the, well, smallest unit of energy, right, of light. Smallest unit of energy of light. So now, if I talk about, well, photon theory, what does it do? It explains the particle nature of light, right? So we understand that light exhibits dual nature, right? Dual nature, two natures, wave nature and particle nature. All right. So photon theory tells you about the particle nature of light and of course photons, right? So now if it is telling you about particle nature of light and when light travels with a certain speed, effectively you can think about photons traveling with the speed of light, right? So now think about it, imaginary. Now if these particle-like energy packets, if they are traveling with a certain speed, yes, they are going to have energy and they are going to have momentum. Of course, so photons have definite energy and momentum. We understand that much. We have also learned about what energy of each photon is and what momentum of each photon is, right? So all the photons always travel with speed of light in vacuum, right? And then when light travels through any other medium, of course, the photon speed will be equal to the speed of light in that particular medium, right? So that is that. Now, if we talk about energy of photon, and this is what Max Planck gave initially in his quantum theory. Okay, so this is the building block statement or one of the building blocks of quantum theory, right? What he said was, well, light comes in very small energy packets and each energy packet has equal energy if the light has uniform frequency, right? So energy of each packet depends upon the frequency of that packet. So here I will say that energy is directly proportional to frequency, E proportional to nu, and the proportionality constant over here is H, so E is equal to H nu, and H is the Planck's constant, right? That's why it is called Planck's constant, because Planck gave it. Okay, so energy of one photon is E is equal to H nu, you know that. Now for any wave, well, V is equal to F lambda, so C is equal to nu lambda, and when we substitute this, we get the other form of energy of a photon, which is hc by lambda. Simple. We know this, we've learned this before, and to ease our calculations, because if you look at these constants, right, they are really bad. So see, speed of light, anyway, it's a good number, 3 into 10 raised power 8. But if you look at Planck's constant, it is 6.626 into 10 raised power minus 34 joule second, right? It's a very small number and yes, difficult in calculations. So what we do is we substitute all of these values and we get this shortcut for calculation. Okay, what shortcut? E is equal to 12400 divided by lambda. If you substitute lambda in angstrom, right? Angstrom is 10 raised power minus 10 meter, by the way, right? So if you substitute wavelength in angstrom, you are going to get the corresponding energy of a photon in EV, electron volts. And later on also throughout modern physics, this calculation is really important. So do remember this number, okay? Now we come to momentum of photon. Momentum of photon comes from special theory of relativity that was given by Einstein. I am not going to go there in detail, all right? But what happens is momentum of a photon comes out equal to h by lambda, all right? Now those who are interested in it, please do look at the relation between energy and momentum of a photon, right? And there is a term for rest mass there as well. When you look at that equation, you can easily derive mass of photon is equal to 0. You directly end up getting this, all right? I'm not doing it here because it's not in your syllabus, all right? But it's a very quick derivation. Now, once we get momentum of a photon, that is h by lambda, we can actually do a lot more things right? We can do a lot more other kinds of analysis and calculations. And that is where we are diving back or diving further into photon theory. Okay? All right. Ayush, yes, we have done this yesterday. This is a very quick revision for you guys. All right. Now let's dive into this further. So just now we looked at energy of a photon. We looked at momentum of a photon. Now we are going to look at photon count. Or rather, think about it this way. If I know that there is a source of light which is giving out light in the form of energy packets, all of these energy packets, right? This is how the light is coming out. Okay. Now, if this is how the light is coming out and I know, say, power of this light source, right? I know power is P. What is power? Power is energy per second, right? So, next question comes into my mind that, all right, if this energy is coming in terms of, or rather in the form of these photons, and this much energy, say a 100-watt bulb, right? So, if there's a 100-watt bulb, that means 100 joule of energy is coming out per second. So, then how many photons are coming out per second? Can you find that out? Right? That is what is called photon count. Okay? Photon count is basically number of photons emitted per second by a source. And we can, yes, definitely find out photon count. Just apply common sense and basic understanding of energy. Right? Think about it. Power is energy per second. And this energy is coming in terms of photons. So, if I say that n number of photons are coming out per second, then total energy that is coming out per second divided by energy of one photon will give you number of photons coming out per second. Make sense? That's what we do. We say power divided by energy of one photon will give you number of photons per second. Right? Okay. Sharmila, yeah, if lambda is in nanometer, then divide 1 to 40. Yes, correct. Of course. You can remember both of them. Alright. Now, coming back over here, I can see that photon count, if I substitute E is equal to hc by lambda, right? Energy of one photon, what do I get? hc, and then lambda from denominator goes to numerator, it becomes P lambda by hc, and P is power. Power can also be written as intensity into area, right? Okay. So at any given instant, if I say, all right, this is the area that I'm talking about, say, you know, this is the area through which light is coming out, and I want to find out N over here, then I'll say that intensity over here multiplied by area will give me power, right? So I can replace power with intensity into area as well. Okay, because you all know basic definition of intensity, right? Yes, intensity is energy per unit area per second. There we go. So, N comes out to be photon count, which is IA lambda by hc. Okay, do remember this. Now, as I've told you, we are going further ahead into photon theory. So, we've calculated one thing, right? We've calculated photon count. What else can we do here? Here, we can do one more thing, right? There is one more term that is defined. Photon flux. Alright. So now what is photon flux? Think about it this way. If I have different types of sources, right? So then power variation will be different, or rather intensity variation will be different for different types of sources, right? Say I have a point source of light, or I have a plane wave, or you can say that the source of light is really far away and I have got a parallel beam of light coming in. In these cases, the analysis of the photons will be different, right? So here is what we look at, photon flux, and it is really relevant in later calculations as well. Alright, so what is photon flux? Photon flux is number of photons emitted per second, right, per unit cross-sectional area by the source. Okay, so when we talked about previously, right, number of photons per second only we calculated. Here we are calculating number of photons per second per unit cross-sectional area. Simple? So what do we need to do? Yes, photon flux, we can say that this is equal to what? N divided by cross-sectional area. Simple, right? Okay, photon flux, N divided by cross-sectional area. Now, we already have N value, right? So here I can say that, well, photon flux is equal to P by E, which was N divided by cross-sectional area also, right? So P by AE. Now in here, I can directly say that P by A is intensity. Power per unit area is intensity, right? So I can say that this is intensity divided by E. E is energy of one photon, which is hc by lambda. I can substitute over here. I get I lambda by hc. All right. I lambda by hc gives me in this photon flux in terms of intensity. Now, look at it carefully. All right. Look at it carefully. I can see different people have joined as well. Hello Mehtab, Aditya, Vasu, hi Jitendra. Hey Aditya. Guys, pay attention over here. Okay. So, now calculation of intensity will depend on what kind of light source it is. If I talk about this light source, right? Point source of light. That means what? Light is going in all directions, right? It's going in all directions. That means if I talk about, say, n number of photons coming out per second, they will be hitting a cross section of, yes, they'll be hitting a spherical surface. All of them, right? Okay. So I'll say that at any given instant, if n number of photons are coming out, then they are hitting a spherical surface at a particular moment. And I will say that this area over here will be surface area of this sphere. If I say I take a sphere of radius r, I want to find out intensity at this point, then I will say that intensity is equal to P divided by 4 pi r square. That's what I will go and substitute over here. Make sense? Okay. Now similarly, if I don't have a point source of light, or rather if I have a light that is very, very far away, right? Say for example, sunlight. Now sun is really, really far away. So sunlight, as it comes to us, it seems to be a parallel beam of light, right? Right. So it's a plane wave that is coming to us. And here I can say that, see, this is a parallel beam of light. So rather these photons that are traveling parallelly. And in this case, if I talk about intensity, I will say that photon flux will be number of photons emitted per second per unit cross-sectional area. This will be the cross-sectional area, right? This area. So if I say I've got a cylindrical beam of light of radius r, cross-sectional radius r, then area will be how much? Area will be pi r square. And that is why intensity will be P divided by pi r square. Right? Okay. So now that we get intensity is equal to P divided by pi r square, we can actually substitute over here. We get our photon flux. Make sense? Okay. I hope you've understood this. Now the only caveat here in all of these calculations is that all of these sources of light, right? These are all monochromatic sources. What does that mean? All of these sources of light are giving out light of single wavelength, single frequency. Okay? And that is why all of these photons that are coming out have equal energy. Alright. Hope that is clear to you. Now that we've understood, well, number of photons per second, we've understood photon flux, let's go and understand photon density. Alright. Photon density. Now, what does that mean? Okay, what does the name say? Photon density, right? So, number of photons per unit volume. That should give me photon density. That's it. That's what it is. So, photon density in a given region is number of photons per unit volume, and that region will be what? A light beam, right? Because, well, we are talking about photons. Photons will be present when there is light. Okay, so in a light beam, photon density is number of photons per unit volume in the light beam at any given instant. Okay, so say over here now again we have a monochromatic light beam. Monochromatic, singular wavelength, singular frequency. So Do you understand that here in this light beam there will be all of these photons, right? They'll be traveling with speed of light, all of them, and with energy h nu. You know that. But then how do we figure out how many photons are there in any per unit volume, right? We can do that. We can apply unitary method. Okay. So, alright, Neha Kumari, please explain in Hindi. Of course, Neha, I'll explain in Hindi also. Okay. So, what we can do here is we can look at the basic understanding of how photons are going, right? Photons कैसे travel करते हैं? See, if I assume, well, number of photons that are incident on a cross section per second, right? So now think about it. If this source of light is giving me 5 photon flux, right? I know the photon flux is 5p. Then I can say that in this area, right, in this beam of light, A is the cross-sectional area, and so the number of photons that are incident on a cross-section will be equal to how much? Photon flux into area, right? That will give me number of photons per second. Okay, I know that. So now I can define this cross-sectional area and I can say that, say, these n number of photons were incident or were hitting this cross-sectional area, were passing through this cross-sectional area at t equal to 0, right? So there were n number of photons. Now pay attention, n number of photons passing through this cross-section at t equal to 0. So then if photons are traveling with c speed, then in 1 second they will cover c meters, right? C in meters per second. So I will say that at t equal to 1 second, all of these photons that crossed the first cross section will be now crossing here. Make sense? Okay. So now can I say that in that duration of 1 second, right? In that duration of 1 second, whatever photons crossed the first barrier, let's say this is first cross section, this is second cross section, right? In this duration of 1 second, whatever number of photons crossed the first cross section were yet to cross the second cross section, right? वो second cross section से बाहर नहीं निकले हैं. All of these photons in this duration of 1 second are in this cylindrical region somewhere in between. Make sense? And that is what is giving us the number of photons, yes, number of photons that are in the cylindrical region, right? What is that? Number of photons in the cylindrical region will be equal to 5p into A. Now, volume of the cylindrical region is A into C. Let me erase this portion so that you really see this properly, right? So I can say that I've understood that. You've also understood that. The number of photons that are there present in this cylindrical region is photon flux into A, and volume of the cylindrical beam is A into C, right? Area, cross-sectional area into length, which is C, okay? And photon density will be nothing but number of photons that are there in the cylindrical region divided by volume of the cylinder. So there we go. Photon density rho P will be equal to 5P, flux of photon, into A divided by A into C. A gets cancelled out. I get 5P divided by C. Now 5P we have already calculated, right? This is equal to what? I lambda by hc. So here I can say I lambda by hc divided by C, which is I lambda by hc square. Okay? I hope you've understood this properly. Photon density in a monochromatic light beam comes out to be I lambda by hc square. Do remember this. Alright? Okay. Now that we have done this much analysis of photons, let's get a final, well, another look at the properties, right? And I'm going to, this is just a recap for you because we have covered this yesterday as well. Alright? So, energy and momentum of a photon are always conserved. You know this, right? Once a photon is released from the source, its energy is not going to change, its momentum is not going to change, as long as it is not changing its medium, right? Okay. Number of photons may or may not be conserved. Right. So if you increase the intensity, number of photons coming out of the light source increase. If you decrease the intensity, number of photons coming out of the light source decrease. Now, all the photons of a particular frequency or wavelength possess the same energy irrespective of the intensity of radiation. Yes. So if you fix the frequency, no matter what you do with intensity, the photons will have the same energy, right? Okay. The increase in intensity of the radiation implies an increase in the number of photons crossing the given area per second. I've just told you, if you increase the intensity, number of photons coming out will increase as well. If you decrease it, number of photons will decrease. Simple enough? Okay. Mass of a photon is 0. Actually, rest mass of a photon is 0. But for our intents and purposes, since we do not have special theory of relativity in our syllabus, we will be dealing with, yes, in any scenario for you, mass of photon will be 0. You will take that. Okay? Alright. I can see that Ayush, Ifat, Indrajit, you guys are okay with it, right? Understanding everything? Now, till now, if there's any confusion, any doubt, do ask. Alright? You ask in the chat window and I'll answer your doubts. And even if you don't have any doubts and you've understood everything, do keep replying, do keep the momentum up, alright? So that I'll also have all of this feedback coming from you guys. So, last but not the least, property, charge of a photon is 0. Of course, a photon does not have any mass, does not have any charge. It just has energy. Alright. And now that we have done this much, let's have a question, calculate, solve, tell me the correct answer in the chat window right now. Okay? Come on guys. The question is, find the number of photons per second emitted by a light source of power 100 watt if the wavelength of light emitted is 400 nanometer. Come on. Great. Alright. Kiran, Vasu, Adil, good guys. Okay, so you are understanding everything. Now, quickly answer the question. Quickly tell me what the answer is. Okay? You have to find out number of photons per second. That's it. You know how to calculate number of photons per second. I've given you a very quick calculation shortcut as well, right? Hello, Kajal. You have just joined, is it? If you have just joined, quickly solve the question. Alright guys, tell me, what is the answer coming out? Option A is 2 into 10 raised by 21, option B 2 into 10 raised by 20, option C 4 into 10 raised by 21, option D 4 into 10 raised by 20. Okay, Ifat has already solved it. B is the answer for you, huh? Alright. Now here in these kind of options, right, a lot of the times, you know, you've got to concentrate on what kind of options there are as well. Here you can see that the difference in these options is, well, order, right? So, you do not need to concentrate too much on, well, calculations with numbers. You can just calculate the order and narrow down your options. Right? Okay, Archana also got option B, Kiran also got option B. Okay, alright, you guys are solving. And I told you to take 1 minute for a question, right? Your 1 minute is up. So, again, when you are practicing, make sure you give yourself 60 seconds per question. Okay? Now, I'll go on to the solution and let's see. Okay, a lot of people are coming up with answers. Kiran got B, Swarit got 2 into 10 raised by 20. Yes, that is B. Okay, Vasu got B, Ayush got B, Pratihar B. Alright. Mastan, Bikash. Good job guys. This is a pretty simple question. As you can see, simple application. We want to find out number of photons per second. Power is given. Power is energy per second. So, energy per second divided by energy of 1 photon. That's what we're doing over here. Wavelength is given as well. Here we go. Energy of 1 photon we can actually calculate first. We can say that energy of 1 photon is, yes, 1240 divided by wavelength in nanometers. If wavelength is in angstrom, we write 124000 divided by wavelength in angstrom. Right? Okay, so now that we substituted, we get a simple value. Now this value is in EV, so now we can calculate the number of photons, right? Number of photons is power divided by energy of one photon. Power is 100 watt divided by energy of one photon. We get this answer. Okay. Now here as well, we can see that the other calculation, right, the smaller numerical calculation, you don't really need to do much. What you need to do is look at the power of tens. There we go. So option number B is the correct answer. All right. Let's move on now. Till now, I hope you're understanding everything, right? If you are and you have friends, do let them know about this as well. All of you can attend this class with your friends as well. And when you attend the classes with your friends, right, you can always compare notes. You can always talk about what went on in the lecture. You can always solve questions together. That helps you in studying. Okay? All right. Let's move on now. Let's go to the next subtopic of today, which is, yes, radiation pressure. So now that we've understood, right, how photons behave, what happens with photons, let's first understand more about, well, what is the effect of photons when they fall on certain surfaces, right? Okay. So radiation pressure. Now what is radiation pressure? Radiation pressure is the pressure experienced by the surface exposed to a radiation. All right. So think about it this way. I have radiation falling on a surface, right? Now ideally, if it were just wave falling on a surface, why would it apply a force on the surface, right? Here as well, the wave nature does not make sense, right? This is basically light displaying particle nature. Why? Because I know if I take a ball and I, well, throw it on the table, then the ball will either, well, bounce back or it will stop where it will hit. But in either case, the table is going to feel a force downwards, right? Table is going to experience a force downwards. Same thing is happening over here as well. You've got these particles coming with a certain momentum. When they lose that momentum, they impart a force. That force per unit area gives you pressure. Simple? Okay. That's what we are going to calculate now, right? So force due to these photons divided by area, right? That is what radiation pressure is. All right. So then how do we calculate? Well, before we calculate, let's understand more. The thing is, of course, light consists of photons which behave like particles, and of course, when these photons fall on a surface, they apply a force on the surface because of, yes, a change in momentum. That's what I've just told you. Because of this force, there is a pressure experienced, which is radiation pressure. Okay. Now after this session, you guys are going to get all of these notes, so don't worry about it. Just concentrate on the session right now. Okay. All right. Now let's calculate radiation pressure, right? So how do we calculate that? Let's take the first case now. Okay. So the idea here is that, well, in case of light, in case of optics also you've seen, right? In case of waves also you've seen. When light falls on a surface, it gets reflected or it gets refracted or it gets absorbed, right? Waves, radiation, when it falls on a surface, it gets reflected or it gets absorbed. Now in here, if I say radiation is falling on a black body, and here is where, you know, yes, your already learned fundamentals of thermodynamics are coming to the picture, right? So you know what black body is, right? Black body is a body that absorbs all the radiation that falls on it. So here as well, if this surface is made up of a black body, then if radiation falls on it, right, and light is nothing but electromagnetic waves, yes, so if radiation falls on it, then all of these radiations will be absorbed. Now these radiations are what? Photons basically. There are photons in here. What is happening? All of these photons are being absorbed. So all of these photons, they're coming with a certain momentum, and all of that momentum is being absorbed. Because of that, there is force and pressure. Let's calculate that. Now, if this is a black body, we understand that absorption coefficient is equal to 1 and reflection coefficient is equal to 0. Absorptivity and reflectivity. You remember that? Yes, that's what we're talking about over here. So, if absorptivity is equal to 1 and reflectivity is equal to 0, we can say that number of photons that are falling per second will give you the amount of momentum per second that is falling on it, right? Okay, so I can say that number of photons per second, we have already calculated this. This is equal to Ia lambda divided by hc, right? In terms of intensity. Now each photon has a particular momentum. Initial momentum of each photon is h by lambda is in magnitude. Now momentum is a vector quantity. So I can say that if I take downward as negative, upward as positive, the photons are falling down, their momentum will be minus h by lambda. If they get completely absorbed, their final momentum is 0. So I can say that change in momentum per second will give me force, right? Okay. Momentum imparted per second will be how much? Delta P multiplied by n. Delta P, change in momentum of one photon multiplied by number of photons per second. That gives you change in momentum per second. Make sense? Okay. So, change in momentum per second gives you how much? Here I substitute delta P, here I substitute n, I get Ia by C. This is force, so pressure comes out to be force by area, area gets cancelled out, I get I by C. Okay? Alright. Swagata is asking, ma'am, numerical kab karaoge? Beta, as soon as we are done with theory, we will look at applications and numericals karenge. Okay? Alright. Hello Ankit. I hope you guys have understood what is the radiation pressure for complete absorption of photons, right? Now, for complete absorption in normal incidence, I by C comes out. For complete reflection in normal incidence, what will happen? Right? So the fundamental remains the same, right? Fundamental is change in momentum into number of photons per second. Right? Now in this case, what is happening is the photons are incoming with a certain momentum, which is h by lambda, right? And they are outgoing with equal momentum because they are getting reflected, right? So h by lambda. So here I can say that number of photons per second, we already know this. Initial momentum of the photon, each photon is going to be equal to minus h by lambda because it's in the negative direction, downward direction, and final momentum will be in upward direction, so plus h by lambda. And again, momentum imparted to the surface per second, delta P by n multiplied by n, which comes out to be equal to Ia lambda by C multiplied by 2h by lambda, right? So h by lambda minus h by lambda. And this gives me 2Ia by C. This is force. Force divided by area gives me pressure. So pressure comes out to be 2I by C. Okay? Alright. Hello Ankit. I'm good. How are you? Really enjoying teaching you guys. Okay. Let's move on now. So what have we understood? In normal incidence, when there is complete absorption, radiation pressure comes out to be I by C, and when there is complete reflection, radiation pressure comes out to be 2I by C. Here is the summary of what we've learned, right? For complete absorption, I by C. For complete reflection, 2I by C. Now this is only for normal incidence though, right? What happens in case of partial? By the way, here we have two extreme cases, right? Here we have complete absorption and complete reflection. What if the, material is neither a black body nor an ideal reflector? What if it is somewhere in between, right? A real material, like what happens in real life. In that case, we will use absorptivity or reflectivity, whatever is given in the question, right? So we know that for a material, A plus R is equal to 1. So here as well, I am going to say A plus R is equal to 1. So if A is given, I am going to substitute as 1 minus R. If R is given, I am going to substitute it as 1 minus A. Okay? Alright. Now, for partial reflection, as you can see, right? Here will be force by, well, addition of both the type of photons that are there, right? So say a portion of photons, right? If absorptivity is A, that means a fraction of photons are being absorbed. Okay, so that will give me I by C multiplied by A plus, this is force due to photons that got absorbed. Now force due to photons that got reflected, that will be how much? 2I by C multiplied by, yes, the fraction over here will be R, but then that is also equal to 1 minus A, right? Okay, so what we get over here is, or rather, this is R, and if I write this as 1 minus R, I am going to get a very simple expression over here, which comes out to be equal to I by C multiplied by 1 plus R. Okay, so effectively what have we done? We have said that, all right, out of all the photons that are falling, a portion of it, a fraction of it is getting absorbed, a fraction of it is getting reflected. That's about it. Okay, all right. Now that we've understood this, yeah, I'm going to erase this portion, because this is what you need to remember. Okay, so radiation pressure is I by C into 1 plus R. R is reflectivity of the material. Now, till now we have learned about normal incidence. What happens? Ayush says we can also find in terms of A. Yes, Ayush, you can also find in terms of A. So over here you will just substitute R is equal to A, 1 minus A. Okay, that's about it. So this will become 2 minus A. Inside the bracket you have I by C into 2 minus A. Right. You can remember either of them, whatever you want to. Alright. Now that we've understood, well, what happens in case of normal incidence, right? Yes, radiation is falling perpendicular to the surface. But that's not always going to happen, right? Radiation is not always going to fall perpendicular. Actually, realistically, radiation can fall at any angle. So, now we are going to complicate our scenario a little bit, go to the next step, which is, what if radiation falls at an angle theta, right? So if radiation falls at an angle theta, then you understand that since the momentum of these photons is in this direction, their cos theta component is actually the force that is being applied on the surface, right? So cos theta component, which is what? F cos theta. So instead of F, I have F cos theta. And then what is the area on which this force is being applied, right? Because pressure is force that is being applied divided by area on which that force is acting. So here, to calculate radiation pressure, I can say that, see, this radiation is coming at an angle. So force due to this radiation, right, if it were falling perpendicularly, it would have been in this direction. So force is in this direction, but then the surface is in this direction. So cos theta component, this area, right? So now look at the right angle triangle. Do you see that over here, this A divided by cos theta is the area that we are looking for? Yes. This angle is theta, this 90 minus theta, this angle is theta as well, and A divided by cos theta is the area, effective area on which this force is acting. So A divided by cos theta will come in the denominator, and what we get is I by C into cos square theta, right? I by C, why? Because F by A we have already calculated is I by C, so I by C cos square theta, right? But here as well, you see that this is for complete absorption, right? So what will happen in case of complete reflection? It's just that when you substituted F by A, no, instead of writing I by C, you will write 2I by C. That's about it. So pressure will come out to be 2I by C into cos square theta. Very simple. And now you get the idea, right? Yes. So when the radiation is actually incident at an angle theta, then there is a factor of cos square theta that comes here, right? This is how you can remember it. So I by C into cos square theta for complete absorption, 2I by C into cos square theta for complete reflection. And then what happens in case of partial reflection? Of course, In case of partial reflection, the relation that we got earlier was I by C into 1 plus R, and there is a separate factor of cos square theta. That's about it, right? I by C into 1 plus R into cos square theta. And again, as Ayush just said, what? You can write this expression in terms of A also. So of course, instead of writing 1 plus R, you can write 2 minus A also. Doesn't matter. It's still the same, right? Okay. Alright, Ayush says A by cos theta once again explain. Alright, sure. Okay, let me tell you this. From here also, in this diagram also I can explain, no? So the thing is, this is the beam of light that is coming in, right? Do you see this? This is the beam of light. This is the cross section. Now when you see this cross section is A, and the photons are coming in this direction applying a force F, right? Now, if we were looking at force in this direction, we would have taken directly F. But we have the surface making an angle theta with the beam. That means there will be a component of force that will act here. So which component of force? Cos theta component of force, right? This component of force. This is cos theta component of force that will act here. Okay. So instead of F, we have F cos theta. Now, if I talk about area, because pressure is what? Force by area, right? So in the numerator, I've got F cos theta. In the denominator, area. Now, on the plate, what is the area on which radiation is falling? This is the area on which radiation is falling, right? This area. This area, you can see from the figure, is not equal to cross-sectional area of the beam, right? So now, if I look at the relation between the area on which the beam is falling and the cross-sectional area, I can actually find a right angle triangle. Do you see this? Okay, I'm going to erase this portion and I am going to show you, see, this is the cross-sectional area. Do you see this? This is cross-sectional area. This is the area on which it's falling and this is perpendicular, right? Direction in which the beam is coming. Now, do you see that here we've got a cross section, right? And this is a right angle triangle. If this angle is theta, here we go 90 minus theta. I'm going to change the pen color so that you understand better. Okay. So here is 90 minus theta and here is theta again, the red color, right? Now that we have this theta, we can say that this base of the triangle is A, angle is theta. I want hypotenuse. What will be hypotenuse? A divided by cos theta. So there we go, A divided by cos theta. Make sense? I hope you understood this. Alright? Now that we've done this much, let's move on, and we have, well, looked at what happens when a beam falls perpendicular, what happens when beam falls at an angle, what happens when complete absorption happens, what happens when complete reflection happens, what happens when partial reflection happens also, right? We've covered all of these cases. Alright. Bikash is asking, ma'am, what type of questions come in NEET in this topic? Yes, Bikash, that's what we are going to come to next. Alright. So, we are going to solve a few questions from NEET. Now, here one last case that you guys can remember is that when radiation is falling on a surface which is not a flat surface. Okay, so here if radiation is falling on, say, this spherical surface, then what happens is at different places, right, the radiation is going to, the beam is going to make a different angle. And so we'll have to integrate to calculate the net force, right? You take these elemental rings, you calculate dF on each ring, then you integrate, you get the net force divided by area will give you pressure. Now I know you do not want to go into details right now. So what I will say is the final result that comes out is a very easy to remember result. Okay. The average force that comes out on, well, average radiation force that comes on the surface is equal to I by C into projected area, right? Projected area. Now in here, for this particular sphere, the projected area will be how much? The area, or rather the shadow if we assume this is the light that is falling, if I imagine a screen over here, what is the shadow that will going to be? The shadow is going to be circular, right? It's going to have a circular shadow. Shadow's area will be pi r square. That's it. That's the projected area. Okay? That's about it. And again, here as well, we have three cases. If absorption coefficient A is equal to 1, reflection coefficient R is equal to 0. For complete reflection, 2I by C into projected area. For complete absorption, I by C into projected area. And there we go. Okay? Alright. Do remember this. Now, let's come to questions. So, here we go. I've got a question for you. Quickly solve it. Quickly tell me what the answer comes out. Alright? So the question says, a beam of white light is incident normally on a plane surface, absorbing 70% of the light and reflecting the rest. If the incident beam carries 10 watt of power, find the force exerted by it on the surface. Okay. 4 options are given here. Come on, quickly solve this. And yes, as I've told you, these are the type of questions that come in NEET. Alright? Kiran, for projected area, why don't we directly write pi r square? Yes, we have directly written pi r square only. Alright? Projected area of any 3D figure, right, will be the area of shadow that falls behind it on the screen. You can think of it like that. Okay, so for a sphere, the projected area comes out to be the area of the shadow, which is circular, so pi r square. Yes, projected area is pi r square. Okay, let's go. Let's solve this question quickly. Come on guys, just apply what we've learned till now, right? We want to calculate what? We want to calculate force exerted by it to the surface, right? Not pressure, force. Okay. Incident beam's power is given to us. 70% of the light is absorbed, rest is reflected, that is 30% is reflected. We have to find out force exerted by it on the surface. Come on, quickly calculate. Tell me what the answer comes about. Alright. I can see. Vaishnavi has already solved it. C is the answer, is it? Let's see what it comes out. You're getting C, I can see. Okay. Saugata. Hello. Quickly solve the question. Come on guys. Tell me what the answer comes out for you. And here as well, you can see that, right? Calculations, if they are taking time for you, you've got to practice with time. I will keep saying this again and again because it is really important. Okay? Alright. Come on. Beam of white light. So you know radiation pressure, right? Yes. Radiation pressure is, of course, I by C into 1 plus R. Radiation pressure is I by C into 1 plus R. So what is force? Force is going to be this multiplied by, yes, area. That's about it. Everything else is given. Come on. Tell me what the answer comes out. Okay, let's go to the solution now. Here, you can see that a beam of white light is incident normally on a plane surface. 70% of the light is absorbed. That means A is equal to 0.7, right? 70%. A is equal to 0.7. So R becomes how much? 0.3. 30% gets reflected. R is 0.3. Right? Power is given as 10 watt already. Now power is equal to intensity into area, right? Yes, you know this already. So now I can say that here pressure is equal to force per unit area, which is equal to I by C into 1 plus R. So I by C into 1 plus R is this. Now, since we want to calculate force, we can say that, well, area gets cancelled out. F comes out to be equal to 10 by c into 1 plus 0.3. c is speed of light. There we go. Once you substitute values and calculate, this is what you get. Okay? Alright, I can see Saugata got C, Vasu got C as well. Alright, 4.3 into 10 raised to power minus 8 newtons. C is the correct answer. Of course, good job guys. As you can see, how easy application based questions come, right? Direct application of what you learned. Exactly. C is the correct answer. And now that we've solved this question, let's go ahead and solve the next one. Okay? Here we go. Quickly solve the question. Quickly tell me what the answer comes out. The question is the intensity of direct sunlight before it passes through the Earth's atmosphere is 1.4 kilowatt per meter square. If it is completely absorbed, find the corresponding radiation pressure. Alright, completely absorbed. As you can see, A is equal to 1 over here, right? Yes. Now, intensity is given as well. It's completely absorbed. We want to find out radiation pressure. Come on guys, quickly solve this. Again, very direct application, and this is the type of questions that come in NEET, by the way, right? Alright. Conceptual questions Saugata is asking. Yeah, conceptual questions mostly, alright, we are going to photoelectric effect, right? There will be a lot of conceptual questions coming from there. Okay, so let's solve this quickly. Well, completely absorbing surface, what do we have? A is equal to 1, P is equal to I by C. That's it. I is given, C we have, direct substitution, we get P is equal to 4.7 into 10 raised to power minus 6 Newton per meter square, radiation pressure. Okay, what is this option? 4.7 into 10 raised to power minus 6 is option number B. I can see a lot of you have got it. Kiran, Ayush, Vasu, good job guys. Okay, now with this we are done with radiation pressure. Let's get to photoelectric effect now. Alright, okay, I can see Ifat is back with solving. B is the answer that you got. Great. Now, after this, let's go to photoelectric effect. And photoelectric effect again is a very, very important concept, or rather it was a very, very important experiment that was conducted by Hertz way before photon theory came about, and it was a determining experiment which actually gave rise to the idea of that yes, there might be, well, particle-like behavior coming from light instead of wave-like behavior only. Okay. Alright, I can see other folks have solved as well. Saugata got B. Alright Saugata, I understood. Okay, let's get to photoelectric effect. So, in short, what is photoelectric effect? Photoelectric effect is, yes, ejection of photoelectrons from a metal surface when light of suitable wavelength falls on it, right? So what happens is, when you have metal surface, light of suitable wavelength falls on it, it ejects electrons, right? These electrons that are ejected due to photons, due to light, are called photoelectrons. That's about it. Okay, so if we look at the apparatus, we see that here, see, light is falling, this is the metal plate, and these photons go in, they eject the electrons come out. Now, there is a potential difference kept in this tube over here, because we want to take all of these electrons that are coming out and have them accelerate and fall on this plate, right, plate A, where these electrons get absorbed and we get this current in the circuit, right? Why do we want this? Why do we create this potential difference over here? So that we can measure how many electrons are coming in, are being ejected, right? That's about it. If electrons get ejected and we have no way of measuring, then we can't really figure out, right, experimentally. So what do? We have this tube where there is a potential difference between these two terminals A and C, right? And this is anode, this is cathode. Now, when electrons accelerate, they actually all of these electrons that come out of the metal, they end up going through the circuit, and thereby we are able to calculate how much, or we are able to observe how much current is coming out. And since that current is coming only because of photoelectrons, we understand that, all right, these many photoelectrons came out, these many photoelectrons got ejected. Okay, simple. Now, when the experiment was conducted, there were certain things that were observed. Okay, there were certain observations, and here guys pay attention, because this is where conceptual questions come in the exams. All right, so what happened? First things first, yes, photons were incident, and when we had, well, a certain monochromatic light that was incidenting, when we had a certain wavelength and we were increasing or decreasing intensity, right? So if the wavelength was, well, bigger than a certain number, then no matter what you do to the intensity, the photoelectrons will not come out. That was a very important observation. Above a particular wavelength, no photocurrent is produced even at a very high intensity. Okay, but on the other hand, if I change the wavelength, if I reduce the wavelength to a certain amount, right? If I make it smaller. Now, if wavelength is smaller, that means energy of photons is bigger, right? That's what we have. So, if I take photons, or if I take monochromatic light where wavelength is smaller than a particular number, then even at lower intensity, we are going to get photoelectrons, right? That was the second observation. See, here you can see that at lower or higher intensity, you are going to get photoelectrons. Below a particular wavelength, photocurrent is produced even at lower intensity. So this told us that the energy of individual photons is really important. Okay, so that is where we say that if individual photons contain energy smaller than a minimum amount, that means a minimum amount of energy is required for the photons to have to eject photoelectrons, right? And since energy of a photon is hc by lambda, or h nu for that matter, we will say that threshold frequency will be the minimum frequency corresponding to the minimum energy, right? Below which photoelectric emission is not possible, right? And that is what we say is threshold, that is the minimum value, right? And the concept of threshold wavelength also comes, right? Because corresponding to a certain frequency, the light is going to have a corresponding, yes, wavelength also. So threshold wavelength is again the corresponding wavelength, but then if we're talking about minimum energy, we are talking about maximum wavelength, right? Yes. So maximum wavelength of the incident radiation above which photoelectric emission is not possible. This is threshold wavelength. So we can say that nu naught or lambda naught for that matter will be related, and for nu less than nu naught and lambda greater than lambda naught, emission will not take place. Is it okay? All right. What else then? Well, we have defined the minimum frequency and maximum wavelength, right? Those are threshold frequency and wavelength corresponding to a particular energy of photon, right? Minimum energy of photon. So let's give that a name as well, right? Instead of calling it threshold energy for that matter, what we call it? We call it as a work function. All right. So it has got a different name, but understanding is the same. So work function is minimum energy required to bring out electron from a surface. Okay, it's the minimum energy required to bring out electron from a surface, metal surface. Now what is happening over here? Well, you can see that if lambda naught is threshold wavelength and nu naught is threshold frequency, then phi work function, which is minimum energy, can be calculated using these, right? Hc by lambda naught, this is equal to h nu naught. Simple. And here as well, that shortcut that I told you about, hc, h into c numerical value, this is equal to 12400 when you substitute lambda in angstrom. This should be in angstrom. All right. Work function, threshold frequency and threshold wavelength are constant for a particular metal surface. They depend on the material, on the metal. If you change the metal, they are going to change. If you do not change the metal, no matter which radiation is falling on it, the threshold frequency, threshold wavelength, work function, they are characteristics of the metal surface that we're talking about. Okay? Alright. Now, let's talk more about what happens to these electrons. When these electrons come out, they should have some energy, right? Yes. So, what happens is, well, minimum kinetic energy of a photoelectron, or rather, what happens to a photoelectron? See, a photon goes in, right, and expends certain amount of energy, right? Kuch energy kharch karta hai photon to bring the electron out. That energy that is expended is work function. Beyond which, whatever energy is left out, that will be the energy that the electron is left out with, right? That's about it. Simple math, okay? So, here also there are certain rules of photon theory. So, what is there? One photon can only give energy to one electron, and a particular electron can take energy from a single photon, right? This is what we have to remember. So, the idea here is that one photon is going to eject only one electron. It's not going to say, okay, I have got enough energy, now I can eject 2 electrons right now. No, that's not what's going to happen. Okay? One photon can eject only one electron. An electron can only come out of the metal surface when its energy after multiple collisions inside the metal is greater than the work function. Right? Okay. That means, of course, the photon that is ejecting out that electron, if the energy of the photon is greater than the work function, then only it can take out the electron. Extra energy of the photon imparts kinetic energy to ejected photoelectron. As I told you, simple math. That means if 100 was before, 50 got expended in bringing it out, 50 got left. Right? That's it. So, h nu, initial energy of the photon, minus work function, energy that got expended, jo kharch ho gayi, this remains as energy of the electron, kinetic energy of the electron with which the electron comes out. Now again, this is the maximum kinetic energy with which the electron can come out, because electron to immediately it can come out, or it can come out after expending a little bit of energy as well, right? Okay. So we understand that maximum kinetic energy of a photoelectron is equal to half m Vmax square. As you can see, V will be speed, mass will be mass of electron. This is equal to h nu, energy of the incident photon, minus phi, work function. Okay? Alright. Now this simple relation is what you need to remember to solve a lot of simple problems that come in NEET. Okay? Alright. Now, let's look at graphs as well, right? Because these type of questions, right, identifying graphical relation, that also comes in NEET. Okay? So, do remember this. What is a graphical relation between, or right, what is the graphical representation between kinetic energy maximum and frequency, right? Frequency of the photon that was incident. So, we can see that the relation is what? Ke max is equal to h nu minus h nu naught, right? H nu is energy of the incident photon, h nu naught, work function. So, as you can see, these two are related with a linear relation, right? There's a linear relation between them. So, the graph will be a straight line. Alright, this is a straight line graph. This is y equal to mx plus c kind of a relation. As you can see, m is equal to 1 and, or rather, m is equal to h and c is minus h nu naught, right? This is minus phi. Okay, this is relation between kinetic energy max and nu, frequency of the incident radiation. What about wavelength of the incident radiation? We can do that as well, right? Of course. So here's the graph, whether you want to plot it of between kinetic energy maximum and frequency, or you want to plot it between kinetic energy maximum and 1 by lambda. It's going to come out as the same straight line. Alright? Because again, here as well, energy of a photon can be written as hc by lambda, and work function can also be written as hc by lambda naught, where lambda naught is the threshold wavelength. Alright. I hope you understand this. The basic fundamental still remains the same. Basic fundamental is max kinetic energy is equal to energy of one photon minus work function. That's it. Now you can write all of these values in different ways, and that is how you can relate different values. Okay? Alright. And with this, let's solve another question. Here's a question that came in NEET 2018. So quickly solve this question. Quickly tell me what the value comes out. When light of frequency 2 nu naught, where nu naught is the threshold frequency, is incident on a metal plate, the maximum velocity of electrons emitted is nu1. Alright, or V1. This is V1. When the frequency of the incident radiation is increased to 5 nu naught, the maximum velocity of electrons emitted from the same plate is V2. The ratio of V1 to V2 is. Right. Now here as well, you can see that, right? We have two scenarios, right? And they are relating the incident photon's frequency to the maximum velocity that the photoelectron comes out with, right? And we know one simple relation, of course. So quickly solve it. Quickly tell me what the answer comes out, alright? And you can see there are no bad calculations here as well. Very easy calculations, very quick calculations. Come on, quickly solve, tell me what the answer comes out. A, B, C or D. What is the ratio? V1 to V2. Alright. What is the fundamental? The fundamental is basic math, right? Photon came with a certain energy of the photon. It expended certain energy in bringing the electron out minus work function. This is equal to the energy with which the electron comes out. Energy that electron has got left. Kinetic energy max of electron. That's about it. Now, if you are relating with frequency, you can write these in terms of frequency h nu. If you are relating in terms of wavelength, you can write them as hc by lambda and hc by lambda naught. There we go. Alright. Let's look at the solution. K max is equal to h nu minus phi. Right? As I've told you, there are two situations given here. Oh, I can see Ayush has already calculated A option. Saugata got A as well. Alright, let's see what the answer comes out, yeah? Anybody else? Vasu got B, Saugata got A as well. Okay, Vaishnavi got A. Saugata is asking graph repeat kariye. Okay, what I can say is you are going to get these notes with you. Alright, and in the graph you will see that it's a straight line. Relation between kinetic energy and nu. See, it's straight line, right? Y equal to mx plus c. This is also you can see. That's it. Okay? Alright, Maksud also got A. Let's see. So there are two cases here, right? What is the first case? The first case says, yes, half m v1 square, because v1 is the velocity with which electron comes out. So half m v1 square is equal to h times 2 nu naught, because initial frequency, or rather frequency of the incident light is 2 nu naught, minus work function. Work function will be h nu naught, because work function is h into threshold frequency. This gives me half m v1 square is equal to h nu naught. Let it be equation number 1. Now let's go to case 2. Case 2 says that, well, half m v2 square, the second case kinetic energy, is equal to, yes again, energy of the photon minus work function, energy of the photon h into 5 nu naught, because, well, the second time the photon had 5 nu naught frequency, minus work function, which is h nu naught. There we go. 5h nu naught minus h nu naught gives you 4h nu naught. Second equation. What do we do with this? We want ratio. Let's divide. Once we divide them, we get v1 square by v2 square is equal to 1 by 4. v1 by v2 is equal to half. The ratio of v1 by v2 comes out to be half. So, if you look at the options, option number A is the correct answer. Right? So, all of you who got A, good job guys. And see, this is, you can see how easy these questions are, right? Direct application. As long as you do not make any silly mistake, as I've told you, remember the basics, remember the basic formulas, and don't make calculation errors. You are going to score in this topic. Okay? Kiran is asking, is it 1:2? Yes, Kiran, it is 1:2. Let's move on now. Let's understand more about photoelectric effect, right? And here as well, again, we come to certain observations based on which a lot of conceptual questions come. Okay, not a lot of numericals, but a lot of conceptual questions. So, do pay attention. All right. Now, what else happens in photoelectric effect? See, we understand that, well, photocurrent comes out, right? But then we have a lot of different things to do in here. We can increase, decrease intensity, right? Does photocurrent get affected? What happens there? Let's understand more, right? So, photocurrent, as you can see, right? Intensity is energy per second per unit area. So, if I increase intensity, effectively, in this beam of light, I am increasing the amount of energy that is coming out, right? Amount of energy per second per unit area. That means the number of photons per second per unit area are going to increase, right? Photon flux is going to increase. If number of photons increase, that means these number of photons will eject more number of electrons. So, what can I say? I can say that photocurrent is directly proportional to intensity of light. If you keep increasing intensity, photocurrent will increase. Okay? Alright. What else? Let's see how this graph comes about. Right? So, next is saturation current. Now, what is saturation current? See, for a particular intensity, right, as I've told you, if you increase intensity, the more number of photoelectrons are going to come out, right? But photocurrent and the number of electrons that have come out, yeah? Pay attention here. This is important to understand. Amount of photocurrent and the number of electrons that have come out, they might be different. Because, see here, in this tube, right? Do you see this? In this accelerated tube, if I have these electrons that are coming out, but they are not reaching the anode, then they will not contribute to photocurrent. Do you see that? It might happen that, say, 100 electrons came out, but only 80 electrons reached the anode, contributed to photocurrent, but 20 electrons remained over here, ya hawa mein, in the air somewhere, right? Or not air, actually, this is filled with noble gas, so yeah, but in the region. So, what happens is, as you increase the potential difference applied over here in the tube, right? As you increase the potential difference, more and more electrons get accelerated, more and more electrons reach anode and contribute to the photocurrent. And that is what you can see over here, right? You can see that if you keep increasing to a certain potential, right, there will be a certain potential beyond which photocurrent will not increase, right? After all of these 20 lagging back electrons also come into photocurrent, there will be no more electrons to increase, right? That's it. So for a given amount of intensity, as we increase the potential difference, see, as we increase the collector plate potential, the photocurrent increases to a certain amount and then it reaches a saturation value that is called saturation current. Now, on the other hand, think about it this way. If I reverse the potential difference now, okay, if I reverse the potential difference, instead of accelerating the electrons one way, I start applying the potential difference in the other direction inside the tube. What happens then? What happens is, even if electrons are getting out, ejected with a certain kinetic energy, if they encounter, right, if they encounter an opposite direction potential, then they might still get retarded and not reach the anode. right? If they don't reach the anode, the current over here, photocurrent that is measured over here in this circuit goes down. That's what happens over here, right? And if you keep increasing this opposite potential, then there will come a certain point where all the photoelectrons will not be able to reach anode, right? That means that is the potential at which the photocurrent has stopped, and that is called stopping potential. Okay? When all the photoelectron reach plate A, the current reaches maximum value, but then if you do reverse, right, if you apply potential in the other way, you will see that at a certain negative potential, in the opposite direction potential, there will come a point where the photocurrent will decrease and become zero. None of the photoelectrons that have been ejected will be able to reach the anode, and that is what the potential, that negative potential, is called stopping potential. Okay? Now, negative potential of plate A at which the photocurrent becomes zero is called stopping potential. So this is the graph that comes out. If you keep changing the collector plate potential, this is the variation in current that comes out. And this is variation at a particular value of intensity. Alright? Okay. Now if I want to figure out what is stopping potential, then can I say that if the highest kinetic energy electron, right, the electron that got ejected with the highest kinetic energy is actually going towards the anode, if I am able to stop that particular electron, then we can stop all the other electrons as well, right? You have to stop the fastest, then you would be able to stop all the other as well. Okay, so kinetic energy maximum kinetic energy of the ejected photoelectron is E into V naught, right? That means we are deaccelerating the highest kinetic energy electron. We'll be able to deaccelerate all the other electrons as well, right? So K max is equal to E times V naught, and V naught is the stopping potential. So what is V naught then? K max divided by E. K max is equal to, yes. So V naught is equal to K max divided by E. Now K max is nothing but energy of a photon minus phi, work function. Energy of a photon is h nu minus phi is the work function. There we go. This is stopping potential. Understood? Alright. Now that we have understood what happens in stopping potential, let's see what happens when we change intensity now. As you know, intensity is directly proportional to photoelectron, number of photoelectrons that are ejected. So of course, in this graph itself, the amount of photocurrent will increase. As you can see, I1, I2, I3, different intensities. As you increase the intensity, the graph goes higher and higher and higher, right? But the shape of the graph will remain the same because the behavior of photocurrent with collector plate potential will remain the same. Okay? And you can see that since stopping potential only depends on the frequency of the incident radiation and work function, right? Stopping potential is equal to h nu minus phi divided by E. H nu minus phi divided by E. That means stopping potential does not depend on intensity at all. So for all of these graphs, as you can see, stopping potential will remain the same value. If you change the frequency of an incident radiation or change the work function, or rather the metal that you're dealing with, then only stopping potential will change. Okay. Now that we've understood this, let's understand more, right? So, at a given frequency of incident radiation, the stopping potential is independent of its intensity. That's what we talked about right now. And stopping potential is more negative for higher frequencies. Of course, the higher the initial energy of the kinetic energy, the higher the initial kinetic energy of the electron that got ejected, the more negative potential you will have to apply, right? That's about it. Okay. Now, let's understand more graphical relations, right? So, what happens or how is stopping potential and frequency related? See. Again, stopping potential and frequency, they are Well, there is a direct relationship between them, right? It's a linear relationship. As you can see, V naught is equal to h nu minus h nu minus phi divided by E, right? So you've got a linear relationship. That means the graph between stopping potential and frequency of the incident radiation comes out to be a linear value. Now, why I'm doing all of this, why I'm showing you all of this, because these graphs can be directly asked in the exams. Alright, so do remember these. Now, if work function changes, if the metals change, then work function is going to change and the graph will have, yes, the same amount of slope but different C, right? Okay, y equal to mx plus c when you say, m will remain the same but c will change. Alright, y-intercept will change because y-intercept is equal to minus phi by E, as you can see over here. If phi changes, metal changes, work function changes, then y-intercept over here in the graph will change. Alright, so stopping potential and maximum kinetic energy of photoelectrons varies linearly with the frequency of a given photosensitive material at constant intensity. Stopping potential is more negative for higher frequencies, of course, we've seen that, right? Okay, now let's finally conclude everything. Okay, so stopping potential, of course, you can see the dependence of stopping potential on frequency and wavelength of the incident light and on work function. Saturation current depends on intensity of the light. As intensity increases, saturation current also increases. You have seen that. And here I have a table for you. Prateek says repeat. Alright. What do you want me to repeat? Hello Ashutosh. Hi Andrasi. Okay. Here I have this table for you that will make it very easy for you to understand the relations. Alright. How the dependency goes. So, if work function remains constant and intensity remains constant, what happens to frequency, what happens to Vs, stopping potential, and what happens to saturation current, and so on and so forth, right? So, I am going to give this as notes. Do keep it with you. This table will help you a lot, okay? Alright, this will help you in keeping all of this information that we just went through together. And now I hope you have understood everything really well, right? And as I earlier told you that there will be, yes, a lot of conceptual questions are asked from this topic. So let's take a look at a question from previous year's NEET. Yeah? So here we go. Quickly solve this question. Quickly tell me what the answer comes out. Come on guys. NEET 2013 was the NEET in which this question was asked. The question is very simple. Quickly apply the concept and tell me what the answer comes out. Yeah? Source of light is placed at 50 centimeter from a photocell and stopping potential is found to be V naught. If the distance between the light source and photocell is made 25 centimeters, the new stopping potential will be. Come on. Tell me what the answer comes out. Source of light is placed at 50 centimeters from a photocell. The stopping potential is V naught given here. If that distance is decreased to half, then what is the value of the new stopping potential? Come on. Prateek, ma'am, please take question practicing. Of course. We will have further practice question practicing sessions also. And right now I will say, after watching this session, right, after going through this session properly, go and practice the questions that you have right now. Alright, go practice the questions from previous years NEET already asked questions. Alright, and give yourself only 60 seconds to answer questions. Alright, I can see people have already solved it. Prateek says B, Kiran B. Alright, V naught. Ifat also says B, Bikash says C. Okay, let's see. This again, you just need to understand that what does stopping potential depend on. See, stopping potential is h nu minus phi divided by E. H nu minus phi divided by E. Now, do you see that it depends on energy of the incident photon, it depends on work function, but it does not depend on distance of the light source, right? There we go. Stopping potential is independent of distance. Intensity will change, right? As the distance of the light source changes, intensity will change, but stopping potential will not change. So, stopping potential will remain the same, V naught, and as you can see, option number B is the correct answer. Okay? Alright. Devendra, acha, you want session on rotational motion? Yes, we'll do that. After completing 12th grade topics, we'll come to 11th grade topics also. Alright, because well, in NEET, all the topics are asked, right? Yes. So we'll do that, don't worry. And with this, I'm going to end this session. Here I've got a good mind map for you guys, a good summary for you guys. So do take a note. What do we have here? We've got energy of photons. We learned about it. What is the energy of photon? H nu, hc by lambda, momentum of a photon, photon count, photon flux. Number of photons per second is photon count, number of photons per second per unit area is photon flux, and then photon density, number of photons per unit given volume of the beam. Then we learned about radiation pressure. There is one relation that you can remember, which is pressure is equal to I cos square theta divided by C into 1 plus R. Right. Now in here, if you substitute theta equal to 0, you're going to get the perpendicular incident wala case. Okay, and here itself, if you substitute R is equal to 0, it's going to be perfect absorption. If you substitute R equal to 1, you're going to get perfect reflection, and so on and so forth. So basically all the cases can come from here. Okay, do remember this. After learning about this, we went to photoelectric effect, what is threshold frequency and wavelength, what is momentum of a photon, Einstein photoelectric equation, right? Basically tells you about maximum kinetic energy of the electron, and different graphs that we have learned as well. So you will get these notes and do remember these. What is the relation between photocurrent and intensity, saturation current and stopping potential, intensity and frequency on stopping potential, and last but not the least, stopping potential versus frequency graph. Alright? Okay. So do practice. Bye-bye. Happy learning. See you in the next session.